This is going to be a short video on running and interpreting a basic expression analysis in Jump Genomics. You can run this analysis for anything that's expression type. So if you're collecting continuous information based on markers, this is the type of analysis for you. So the easiest way to run this in Jump Genomics is using a built-in workflow. You can do this by selecting different components from the other options, or you can use our built-in workflow. So I'm choosing the basic workflow, and I'll choose the basic RNAseq workflow. There's also a basic expression workflow if you've got not RNA-seq data or a microRNA workflow, but I'll choose the basic RNA-seq workflow. They'll be very similar to the others, but with some unique options specific for RNA-seq data. I'm going to pre-populate this with an example like you see here. To get to this example, if you want to follow along, you scroll to the bottom, click the load button, and you'll see this example is built into the software. So you click OK, and when you click OK, you'll see the same thing populating here. So this example data set, if I click the open button next to where we're referring to it, this is where it lives. When I installed Jump Genomics on my machine, it put it in the program files in the SAS home in my Jump Genomics folder. And then in the subfolders, and then the name of the data set is this sam_mus_ blah 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 .sas7bdat. So if I click the open button, I can see what these data look like. And here's a tip with using Jump Genomics. When you bring data into Jump Genomics, you're actually saving it as a SAS data file. So that's why it had that funny extension .sas7bdat. That's a SAS data file extension. So you're looking at the data in Jump. Right now we're seeing it open in Jump, but we're saving it as a SAS data set. So when you're looking at something in Jump, if you make changes, make sure when you save those changes, if you do file save as, for example, that you save that as type SAS dataset with this extension, .sas7bdat. Don't save it as a Jump data table, save it as a SAS data table. So our data set looks like this. We've got information about the samples in the columns in this case. So this data set has a lot of rows to it because the rows are the markers, and then it has a few columns to it because we only have a few samples. This is a simple example so that it will run quickly, and there are only 6 samples. The data in these columns are actual numbers, so these are the actual counts. And when we have count data, or if we had some kind of luminescence data or some other values here, very often if we looked at the distribution of this, so if I looked at analyze distribution and just for this sample across all of the markers, I might want to look at this distribution in the horizontal layout. You can see that it seems like it's got quite a long tail. In fact, it's so smushed up in one section that there's just a big bar. If I just want to stretch this out and view this a little bit more clearly, I can do that by dragging this. If I want to change the size of the bars, I can do that with one of these tools like the grabber. So I could grab the grabber and I can scroll up or down to make the bins different. These are just really cool jump tools that you can use, but this lets me see that we've got some kind of a distribution that's got a very long tail. So this is not normally distributed data. It kind of gets a little bit approximately normally distributed as I get lower in the distribution, but then it's got that super long tail. For data like these, we typically want to take the log2 transformation. So we're going to have an option to do that in a moment. So we're starting with raw count data, and then we're going to take a log2 transformation. Very often you're bringing data into Jump Genomics already with that transformation. So if you have already got the transformation, then I'll give you a hint at one point where we want to not select to do the transformation again. So on the experimental design tab, we have a second file that gives us one row for each of our 6 samples. It's got to have the array, which basically says we have 6 different samples. You don't need to have array data, but you do need to have a column that says array that's marking your unique samples. And we need to have something like the column name to match up to our other data set. So if we look back at that other data set, we had column names that said CAS1, CAS2, DOM3, DOM4, MUS5, MUS6, and we need something here that matches that. So the column name is going to match the description of the sample back up to the actual sample in the other data set. So if you need help building that in Jump Genomics, there is under Import an experimental design file, a spot where you can help create the design file from your data set. So it'll help you build that yourself, or it's a small data set. You can also just go to File, New, data table and you can build it yourself. Just remember to save it as a SAS data file. Okay, so under experimental design, we have this experimental design file. We could choose things to color or label by, but we're just going to go with the defaults for this example. The QC and normalization gives us options for what we want to see for QC and normalization. And here is that very important, do we already have a log2 transformation or do we need to do it? And we do not have a log2 transformation, so we want this checked. The check says, please do the shifted log2 transformation. The shifting is because if you had zeros, if you had a count of 0, when you try to take the log2 of that, that will be undefined. So you've got to shift it slightly and then take the log2 of it. So 1 is a pretty common shifting factor, but you can choose a different value if you have something else in mind. And if you want to learn more about this, you can click the question mark. Then for the normalization method, we have a lot of normalization methods appropriate for RNA-seq data. So some of these methods, IQR, mean, median, some of these are appropriate for lots of different types of data, and some of these are unique to RNA-seq data. So you'll see different options if you're using a different method. And then we'll run the QC both before and after normalization so we can see the differences. Then for ANOVA, we're choosing how we want to set up our ANOVA model. So our ANOVA model has mouse type as our one effect. So we want to compare between the Cas, the DOM, and the MUS types of mouse. If we had random effects, we could include that here. So there's a lot more we could do with this, but we have a very simple model. We also can switch this type to a count data. Count data will assume a Poisson distribution, or we could specify a different distribution. For example, if we had negative binomial. So if we wanted to treat this in a different way, we could treat this with a different distribution. I'll run just a typical continuous normal distribution because after the log2 transformation, I think that's going to fit well on these data. There are some more data filtering choices and also some options. I'd like to include fold changes in addition to the log2 fold changes. This is going to give me the real fold change. So I'll see the differences on that log2 transformed data, but then this will transform it back to the raw data. For LS means, I can look at any types of differences. We'll go with simple differences right now. With just one variable. This is not a very complicated idea. We also have the difference chooser. If we did have complicated choices to select between, the difference chooser can help us choose only the comparisons that we really want to make, that we're really interested in. So for example, if I only want to compare Cas to DOM and Cas to MUS, I don't care about DOM and MUS compared, I can ask only to include these. If I want to include Cas to DOM and Cas to MUS, but I want them in the opposite order, so DOM minus Cas, I can reverse the order. So I can include them and I can do them in the swapped order, not the order they're set here. So when I want this, I click Save, and then I have those differences selected. But I actually want all of the differences, so I won't use that in this case. Then for the multiple testing, false discovery rate is a very common method to use for the fact that we're doing a different ANOVA for every marker. So we need to do multiple comparison adjustment, but you'll see we have lots of other options as well. And if you have annotation data to carry through the analysis, you can point to a data file here and you can describe that annotation data. And then as you filter your data down to just the significant markers that you care about, all of that annotation stays with it and it packages it up really nicely if you need to take it to another type of analysis, like a pathway analysis. So when we're ready, I hit Run. JMP Genomics is working its way through the different pieces of that workflow. So the workflow was calling to several different components, and the software is showing us the process. And in the end, we get this workflow journal popping up, which shows us all the results. So those are all the components that our workflow contained. In the end, we're getting the ANOVA. That's the final answer. That's what we really want. But along the path, we get a basic distribution analysis just of the raw data. So we see a curve showing the distribution across all the markers. So very similar to the distribution I showed of the first sample. If I hover, I can see that this particular sample is MUS6. It's the one that behaves more differently than the others. So I can click on a sample if I don't like that sample and I think it's too different. Something's gone wrong with that sample. It's got errors in it. I feel like there's something very fishy about it. And I can click on this Create Subset Experimental Design Dataset Excluding Selected Curves. So if I were to do that, now it's going to make me a new dataset. It'll tell me where it put it. I can copy that, so I can just Control-C and dump it back into the experimental design file spot in that original as I was building my analysis. And so what you see is it just took that experimental design file and it removed one sample. So if I need to click on something to filter it out, I can. There's also the box plots view of this. Same information. We're looking at, are the centers all kind of lined up near each other? And are the spreads very similar between all of these? So that was the distribution analysis. If I did decide to exclude something and I wanted to just start working my way back through the analysis one piece at a time, I could then click to data standardize at this point to do a correlation in principal components, to filter on intensities. Anything that I might want to do after this, I can launch as a follow-up process. But I actually already set up my follow-up processes. So the next thing I want to look at is the correlation and principal variance components. And so I get this 3D plot with not a lot of data. I'm not really seeing a huge pattern. There's only 2 points per group. But with more data, I can spin this around and sort of see how the dimensions appear. I see that same information on a 2D plot. If I hover over something, I see what that sample is. Or if I click on it, I can select it and see it show up everywhere else. So this particular sample was Cas1. And so again, everything is interactive. As I grab a couple of these, I can see where they show up in all of the other distributions. If I want to resize something, I just grab the bottom corner to resize it. Again, there's an option to exclude a point if I realize that something is behaving differently than everything else, and I think it might have an undue influence on my analysis. The scree plot shows me, as I add principal components, how much of the variance I'm capturing in all those markers. So with just one principal component, I'm explaining 31% of the variation in the markers expression. With 2 components, I'm explaining 50% of the variation. The correlation heat map is showing me how these guys are related to each other. So I have unselected everybody here, so nobody's highlighted. And so I see that Cas1 is totally correlated with itself, and Cas2 totally correlated with itself. So across the diagonal, red, 100% correlation, because that's with itself. Things that are off the diagonal, if I hover, I can see what that relationship is. So this is Cas2 with Cas1, and they're barely correlated at all, negative 0.029. So the gray things are basically not related to each other. The red things are highly correlated with each other, and the blue things are highly negatively correlated with each other. So MUS5 and MUS6 have a negative almost 0.4 correlation. I see this information in the distribution as well. Everything is interactive. If I select something, I can see everything connected, but this isn't especially informative output, so I'm not going to do more with this right now. And then we can also see this in the SAS output. Now we do the normalization. This particular normalization method has some output to show us what was happening with this TMM version of a normalization. You would not get the same output with something simple like a median normalization. Then we would do the distribution analysis again. So when we do it again, notice that the curves are a little bit closer to each other. So we've still got one that's a little bit off, but it's, I think, a different one now. So if we try to line these up and look at the first one with the second one, a bit tricky for me to do this without expanding it accidentally, but we can look at the tops of them and see that before we had one that was farther off, now we've got everybody shifted a little bit closer together. So our normalization was somewhat successful. We only had 6 samples. They didn't look terrible to begin with, but we did something, and maybe that was a positive. Now let's look at the correlation and principal variance components and see if we learn anything new or different. So we can see the same output again, scree plot again. Everything looks rather similar. The correlation, we're not seeing a different story here. We see the same relationships. So this is probably a reasonable normalization. We didn't mess anything up. We just made the data a little bit better fitting to our assumptions. And so then we finally do the ANOVA. And this was the whole goal. So hooray, we've reached the end, but now what do we do with this? So now we're getting automatically some volcano plots, and in these volcano plots, we should be able to see which markers give us a statistically significant difference. Now we got this pop-up message that said, uh-oh, we had no significant differences at the cutoff of 5.31, and you see that 5.31 up here also. It says horizontal reference line drawn at negative log 10 of the p-value equals 5.31. That negative log 10 of the p-value is just a version of the p-value. We're just taking the negative log 10 of the p-value. The reason for the negative log 10, and that's what's plotted on this side of the axis, the reason for this negative log 10 is because p-values of 0.000001, 0.00001, 0.001, 0.0000001, it's hard to really see the difference between those, especially when you're only reporting them to maybe 4 digits. How would you know the difference between something that had 5 zeros and something that had 15 zeros? So that minus log 10 is actually essentially answering that question. It's saying we're looking at a p-value that's got essentially 5 places after the decimal point. So this is like 0.00001 is approximately this equivalent p-value. This p-value is determined by the false discovery rate. So instead of comparing it at 0.05, we choose something much tinier, and then this is the minus log 10 version of that p-value. However, in our case, we still had nothing hit that threshold. So we want to see that threshold. Our plot over here only goes up to 4.5. I want it to go up to at least 5.3. So I'm just going to drag the top corner until we get to 5.3. So here you can see there's a dotted line at that cutoff. I can make the same dotted line down here and down here. Those will show up automatically as long as you've got data above them, but we didn't. So this is the problem. We set a cutoff. We said this is the place, if you get something more significant than this, that's a marker we care about. And the answer, unfortunately, in this data is there was nothing significant to find. We couldn't find anything at our threshold. So this should be our answer, is we couldn't find anything statistically significant at the overall family-wise error rate of 0.05 using a false discovery rate. We have a minus log 10 p-value of 5.31 for comparison, and nothing was significant at that level. However, for the sake of this example, I will enter a different minus log 10 p-value so that we can see something become significant. So let's try entering maybe 3.5 instead. When I refresh this, it moves the line down to 3.5. And so now I see that this guy, row number 217, this guy has a statistically significant p-value when I'm comparing to that 3.5 for the minus log 10p. It tells us this is row 217, so our marker that's listed in row number 217, and I can put any labels I want here. So if I have a better name than just row number 217, I can put that label as my label here so that I can see what marker it is if I have a better name for the marker. And this tells me that the difference of the mouse type Cas minus Dom is minus 2.11776. So that tells me that the difference in that log2 expression, so the average log2 expression for Cas is 2.11776 lower than the average log2 expression for Dom. And then the third line, the minus log 10 p-value, is saying, well, that was significant at that 3.5 for minus log 10 of p-value. The value is actually 4.6. So while Volcano Plot is showing us what we want is stuff in the top corners, the bottom axis, the x-axis, is showing us the size of the difference. And so this is not actually in fold changes. This is in, if we did this value to the second power, that would be fold changes. So we'll see that in a moment also. But the way we're plotting these here is just in the difference of the log2 expression. So we want these as big as possible, either positive or negative. So this guy actually has a smaller difference than this guy does. This guy's a little less significant, but it's actually got a bigger difference in Cas versus Dom. Here the difference is minus 3.3. Here the difference is only minus 2.1. So either of these guys might be interesting for us to follow up on. I can use my mouse to kind of click and select these two. Let's see if they're significant in the other comparison. So these two markers are significant in Cas versus Dom, but they're not significant in Cas versus Mus because nothing was. And one is significant in Dom versus Mus, one is not significant in Dom versus Mus. We can see the same kind of information by looking at a Venn diagram. So if I grab all three comparisons and say, okay, I'm seeing the same information. There is one marker that is in common. It's statistically significant for Dom versus Mus, and it's statistically significant for Cas versus Mus. So when I click on this, I see that guy highlighted. It's in the overlap of DOM versus Cas and DOM versus Mus. We see one marker that is statistically significant just in Cas versus DOM, not in anything else, and those are our only two markers. So at this point, I can select the particular markers that I care about. So I can, there's nothing in this box, but if this was something I cared about and there were some numbers here, I could click this. So I can select as many of these categories as I want. And when I say, yeah, these are the markers I'm interested in, then I click this Show Selected Rows. So now I actually only have two markers. Those are the only two things that are significant in any of my comparisons. And these two markers are my two, so this row is the only marker name I have for them. But I could carry through whatever marker name information I have in my actual data set. And so then I see all this information about them. So all this information, some of this is going to be important to me to carry into some other type of analysis, maybe a pathway analysis, maybe identifying them in a genome picture. So there's a lot of other things I can do from this point. But the point of differential expression analysis is this, to figure out which markers matter. So now I have the answer, which markers matter. But if I want to look a little closer at these guys, one thing I can do is double click in this row to see all the information just on one page. So this tells me things like, okay, this was marker 217. Some stuff about the fit statistics, the R squared, that's an amazing R squared, it's almost 100%. More stuff about fit statistics, AIC, corrected AIC, BIC. Down here at the LS means is kind of where the interesting stuff starts. So this is saying for this marker, the LS mean is an estimate of the mean that I would expect for the log2 expression of Cas. So here we're seeing that the estimated mean of the log2 expression from the Cas mouse type with this marker is 1.36. The estimated mean expression for DOM is 3.48, and the estimated expression for Mus is 1.9977, basically 2.0. So I can see that for this marker, DOM has a high value, Mus has the next highest value, and Cas has the lowest value. And Cas and Mus are pretty close. DOM is really dominating. I see that same information in the standardized LS means. Now, if I look at this minus 0.8, 1.1, and minus 0.26, these guys together will add up to 0. So this is saying compared to everybody averaged together, DOM is still 1.1 more than the average of all three. And Cas is 0.8 less than the average of all three, and Mus is 0.26 less than the average of all three. So the LS means alone are just what is the mean of the log2 expression for this marker, for these different groups. The standardized or standard LS means, these are compared to all three groups averaged together. Then the differences are saying, okay, take those expression values. So for Cas minus DOM, take the LS mean for Cas, 1.36, take the LS mean for DOM, 3.48, and do the subtraction. So 1.36 minus 3.48, that gives us minus 2.1177, blah, 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 blah. So this is the difference in the log2 expression for Cas versus DOM for this particular marker. If we take that difference and we take that to the second power, so if we exponentiate it to the second power, then we get this value. We get the positive version of this value. So if we take that 2.11 and we exponentiate it to the second power, so 2.11 squared, we're going to get 4.34. And if we give that a negative because DOM was the greater, this is the actual fold change back on the raw data. So this is saying the expression for DOM is 4.34 times that of the expression for Cas. So DOM expression is a fold change of 4.34. So that's 4.34 times as expressed. This marker gets 4.34 times as expressed for the DOM mice as it does for the Cas mice. And if you've tried to use these as likely or more likely kinds of words before, this is a tricky spot too. So this is 4.34 times as likely, which is the same as 3.34 times more likely. So this is 3.34 times more expressed, or a fold change of 4.34, so it's 4.34 times as expressed as in CAS. So that's kind of the basics of what we'd really want to interpret here. If you wanted to make more plots just of your final significant results, you can go back to the ANOVA output and you can ask for lots of ways of filtering this. So you can ask to filter this. Let's see, we could expand these guys by grabbing this corner. We could expand them by changing the frame size up here. We could filter these here. Anytime we just want to look at the data differently, there's always a local data filter. Anywhere you see a red triangle, there would be a local data filter available. So we could filter, for example, on these guys, the fold changes. So let's just choose these 3 fold changes to filter on. And I'll click an add button. So maybe we want the fold changes to be somewhere outside of the range of -2 and 2. So first I'm putting it in between, and then I'm going to click. When I click the inverse of that, you can see that it takes away the things where the fold change was less than 2. And so now I'm seeing my plot updated just for what I'm looking for. So you can apply filters anytime you want. When you want to output some of these graphics, so maybe I don't want these, I'll clear this, I'll take this back off, so I'll say remove local data filter. We're back to the raw data. Maybe I want to put the label on this guy, so I can hover over to where this pin is, and I can label this row, and I can label this row. If I had better label information, these would be a little better looking. Maybe I'll move this guy down here. So if this is the final picture that I want, this is the final picture that I want, this is the final picture that I want, I can also change the colors of things, change the axes, put more markers in here, put more labels. There's tools up here. If I wanted to annotate something, I could click annotate and click a little, put a little note in here and have it say something. So there's lots of things I can do. So I can move a note around or add an extra legend. So when I'm really happy with everything I've got, there's lots of ways to save this out. One simple one is to just choose Save As, and save this not as a jump report, but save it as something that's an image file. So an EMF file is a really good choice, so that that the results will be very editable. So an EMF file might be one image file you could choose. A PDF file is another choice you could make. If you wanted to save this as interactive HTML with data, this would hold the data in the background and still let you click around with things. There's some limitations to this with the filtering, so try things. The interactive HTML with data can be useful, but if you've got data that's proprietary or you can't share it, be very cautious with this. This is not something that's protected if you were to put it on the internet somewhere. You can also save things out instead of saving as. So let's put these into a PDF. I'll show you this as a PDF and we'll open it after saving, and let's just save it directly on my desktop. So here's what my PDF looks like. I don't actually need any of this drill down stuff, but here's where I save my ANOVA results and these plots. So there's lots of things you can do to change how they look, and lots of ways you could edit them. Again, if you really want them to be editable outside of the software, saving them as an EMF or some other type of file is a better idea. You can also save results by publishing them to a site called Jump Public. So let's go to public.jump.com and let's look at genomics examples. So for example, if we wanted to look at a trait analysis, a SNP trait analysis, we could look at these results here. So for example, we could click on the volcano plot. If we hover over different points in the volcano plot, we see what these SNPs are, what their labels are. We could filter out to look at just different chromosomes. We could look at the Manhattan plot. Again, we could filter by chromosome, or we could filter by which p-values we want to look at, and so on. So another follow-up process we might want to do from here is a gene set enrichment. So if we had other annotation data that we could follow along with this, if we want to look at the process description of the gene set enrichment, we would have needed an input data set that has at least a significance variable and an annotation column. So this has some extra information. If we had more annotation, it would be optional unless we don't have something about the variable in the input data set. So if you want to learn more about other processes in jump genomics, clicking on that process description. Also, when you want to see what the output would look like, if you click on the output and results, this is what we would get from running a gene set enrichment. We would get these Fisher exact tests, Cochrane-Armitage linear trend tests, and so on. And so it talks more about the other things we could do from there as well. So that was a summary of what you can do briefly with the RNAseq workflow, or a similar workflow for expression or metabolomics or proteomics or any type of continuous measurement sort of associated with a marker, any analysis like that that's sort of going toward the direction of an ANOVA. So looking at the distributions, doing some kind of normalization, looking at those correlation and principal variance components, and then actually running the ANOVA and interpreting those results. Again, everything you do in JMP, you can use these JMP genomics importers, you can use these JMP genomics workflows. Instead of the workflow, you could select pieces from these different components below. If you decide to select your own components, you could actually build your own workflow. From the advanced workflows, there's a workflow builder. So you could pick the components that go into your workflow, and you could repeat that workflow on new data over and over. And then in addition to all the JMP genomics components, you also have the typical JMP components at the top. So if you have data open, you can use our graph builder, you can use analyze and distribution to explore it. So there are more tools up here as well. So I hope you have a lot of success in using and in interpreting the output from JMP genomics. And if you've got further questions about JMP genomics, you are welcome to send your questions to me at ruth.hummel@jmp.com, and I will either answer them or send them on to someone who can get you some help. So I appreciate your time, and I hope that this was helpful to you. Thanks.